All right. All right. Are you guys ready for some hair? Let's go for hair. We haven't done hair for SIGGRAPH.
That's a weird opening.
Yeah, no, let's do some hair.
Are you going to sing and dance? Broadway musical?
No, not that one. So first of all, we're going to switch over to, let's see, I'm going to do input. And yeah, there we go. And I'm going to screen share with application. Wait, where is it? Cancel. Wait, that. I want to screen share. Screen share with, you guys can even see me screen share. Screen share with, there we go. In case you didn't watch the YouTube video, here's the video, and we're going to talk a little bit about this. So first of all, digital domain does a lot of hair. We have a hair system called Samson, and it's, and Samson is really good at modeling and grooming and defining hair simulation, or hair systems, so how the hair looks. But when you're watching this video, hopefully, can you guys see the video? Are you seeing the video? Yes. Should be seeing that. There we go. Now you guys can see the video. So what you're doing is watching this. First of all, they're simulating 150,000 hairs in real time. Now the groom here isn't all that spectacular, but later on in the video they have some actual simulated or more complicated grooms. But the interesting thing here is they're using the real hardcore hair simulation to train this runtime simulation that's running at that speed. That's very interesting. As you know, I'm sort of on this machine learning data-driven kick here. And what they're doing in this simulation is actually using really, really good simulation. Simulation that takes 10 minutes a frame in order to resolve the hair, and then using it to train their system that runs in less than 20 milliseconds. And remember, if you want real time, the 30th of a second is around 33 milliseconds, right? And so like the video game guys know this, they don't talk about frames per second. They talk about how many milliseconds it takes to do something. And that budget is important. So when we're talking about this, we want to be able to do something that looks as pretty as this. Look at the hair flopping on top of the other hair and all that kind of stuff. All in less than 33 milliseconds. So this is the kind of stuff that's exciting. This is neat. First of all, they're not really solving super hard problems. They're letting the offline stuff solve the hard problems. And then they're hopefully getting something that will work in any situation and still look this good. Now remember, 100,000 full strands, 300 guide strands, 50 milliseconds a frame. That's a little bit more than real time, but you know, getting there. The magic number is 30 milliseconds per frame. So again, we're going to see full simulation result versus their result. Looks pretty cool. It's not 100% exact, but it's not bad. It really isn't bad at all. All right, so we're going to stop this because it does go on for a while. If you look at another 4.5 minutes, we want to talk about how they do this. So boop, make that smaller, and then we're going to stop screen share. However I do that, and cancel. Oh, I don't even think I screen shared. That's okay. Okay, so let me just manipulate that, and then I'm going to switch back to the other camera. So those guys, and it's actually a bit tall. So hold on just one moment while I reach up here and scrunch that down. There, that's better. And just now I've made it out of focus. Great. That's okay. Once I get in there, it should focus on. Oh,
Let's try.
yeah. There we go. That's better. Yeah, that's better. Okay, good. Now I'm going to also turn this off so I can see who's watching. No, wait. I'm going to do that, and then I'm going to switch this. And now I don't have to watch myself because I get distracted and I start looking at myself.
Is that handsome guy in the frame?
Yeah, I know. Why doesn't he stop moving his arms? Okay, so right off the bat, one cool, important thing is, like, at Digital Main we have this thing called Samson. And Samson, you've got this character and there's hair coming out of the character and all sorts of stuff. And we use things called guide hairs. Everybody who's ever looked at a hair system knows about guide hairs. Use guide hairs to control how the hair looks. With a hair, you know, typical 100,000 to 200,000 hairs on a human's head, manipulating all those hairs is difficult. You don't want to do that. You want to manipulate a subset of that. And so we typically have guide hairs, a reduced number of these, that control the overall shape, the look of that. And all these blue hairs, the normal hairs, are hairs that are grown out of the scalp, and they have a relationship to the guide hairs to control how the groom looks. Now, forget all that, because this paper is all about simulation, interactive hairs. And they're going to start using guide hairs and normal hairs. And when I first started reading it, I was thinking, wait, those are the guide hairs that you use to do the groom. Those are the grooming guide hairs. No, they're different. We're going to find new guide hairs when we do this. So to pound that home, what do we start out with? Let me get my paper up here, make sure I go through the right things. So very first thing we do is we say, what are the things we have? Number one, we have, at the beginning of this paper, a groom. We own a groom. And that groom is what the hair looks on a static version of the hair. And so when your character has its head pointed straight forward, not moving, we know what the hair looks like. And this is the stuff that our grooming tool would create. This is what Samson would create. There are guide hairs, normal hairs, all sorts of stuff associated with this. We have that. All those guide hairs and normal hairs, we just treat them all as hairs. We don't even think about the guide hairs that used to create the groom. We're going to throw those guys away. Number two, we have a sequence of head motion. So remember, this is going to be a data-driven thing. So at the very beginning, we have how the hair looks. We also have how the hair or the head is moving. And this is all about getting the hair to move correctly as you're moving your head around. So they start off with like 300 or 500 frames of head motion. And this is just typical head motion. You're moving your head around and doing things that are typical for the head. Then, this is the thing, full hair animation sequence. Full on, on there, hair simulation. And you can use whatever tool you want to do this. But we're going to take this sequence of head motion, this groom, and we're going to run it with a full-blown, as accurate as possible, kick-ass hair simulation. And this, they were saying, takes a long time. Their simulation was taking like minutes a frame to produce this, but they were happy with it. They liked the way this thing looked. And so this is the beginning, and this is what we're assuming we have. The goal of this, after all this, is can we analyze this? We're going to do some sort of great big analysis of this and produce a model that produces similar results that run around 30 milliseconds. So that's what this whole paper is about, is this analysis. How can we analyze what's going on inside this hair to produce something that runs and looks very similar to this, but runs super fast? There's some really, really cool ideas in this paper. I was very excited when I was reading this paper because it was like, wow, there's some really neat ideas in this thing. So how do you do it? Well, before we get to the how do you do it, we need to start defining a couple of terms. And so I'm going to erase all this. You guys have that. We're going to define some terms over here. We're going to refer to it a lot. So in our group, or here's how we represent hair. Hair terms. All right. Okay, in our reduced hair model, a hair strand is a B-spline curve. Right? Pretty straightforward, described by a chain of particles. So if I've got a hair head, I have a hair that comes out of there. I've got a certain number of particles that are associated with the hair, and interpolating through those guys gives me a B-spline. Cool. Okay, each one of these particles has a position P, we'll add over it. All right. And a tangential direction, where I'm just going to draw it like this, a little normal direction, a direction T to aid in smooth interpolation in our hair simming model. So each one of these guys comes along, and it's actually a tangential direction, but we're going to do normal because once you have one, you can get the other. A little T associated with each one of these little particles. It's just easier to visualize that you have these guys floating around along with this. Okay? So there's a little frame of reference. Given your neighbor particles and all this, you can build a little 3D rotation matrix around this to say how this hair is traveling. So it's not just position, it's position plus an orientation vector. And we represent the combo of this as S equals the set of P and T, right? So each particle inside this hair chain has a position and an orientation, a sort of reference frame. So far, so good. All right. Now here's where we're going to get some stuff. So, and this is annoying. I'm going to have a little side note. When I talk about vectors, I often like to draw a little bar over there to say that this is a vector versus just a scalar value. In this paper, we're going to throw these guys away. We're going to say all these guys are vectors because it's a position and all that kind of stuff. I want to make sure I stick with the notation of the paper. In the paper, they say since hairs are always attached to a rigid head, we put a bar over the letter to denote the hair particle state at the head's local frame of reference. So is the hair particle state local to the head, right? So this head defines a frame of reference. S bar is the position, not the world space location, but the position of a particle inside one of these hairs with reference to that frame. All right? We refer to S bar as the local coordinate of the hair particle. S is the world coordinate of the hair particle. I'm actually going to try to not erase this because we're going to refer to this a lot. Okay, then there is a transformation T, and this is actually a matrix. These guys are, that's a collection of both a 3D vector, a 3-element vector, and another 3-element vector. This is actually a big matrix. Given a rigid head transformation, this is the head transformation. Then we can create this. S equals T times S bar. And this transformation takes at the position and orientation of that particle and transforms it into the world space coordinate, right? So nothing too crazy here. We just have the head is at the origin pointing down the x-axis or whatever, and this is the position of the hairs at that spot. And T will take the head and put it into the world space, and we just have to drag those hairs, or the particles associated with the hairs along with it. Easy peasy. But they use this stuff a lot, so we have to know where this is. Okay? So far, so good. Now, their basic concept is that we're going to start using guide hairs. Not the same guide hairs in the room. Told you that. We're not going to do that. We're going to use guide hairs to control this, because we want this thing to run in high frame rates. So we're going to have a character, and we're going to have lots of hairs coming off of this character. And what we're going to do is figure out some of those hairs, or figure out something that represents guide hairs. These guys are going to be guide hairs that are going to control most of the hairs. And on the order of hundreds of guide hairs and hundreds of thousands of the blue hairs would be normal hairs. So there are guide hairs, and then there are normal hairs, which are just interpolated along with them. And somehow, as these guide hairs move, we are going to drive the normal hairs as well. So how do we do that? Well, we do it with hair skin.
So the guide hairs are full simulation?
Guide hairs are full simulation, correct. Yes, and that bears repeating. The guide hairs are full-on hairs that are being simulated by whatever simulator you want to, as long as it runs in freaking fast. The guide hairs are going to have collision detection run on them, and they're going to behave like nice hairs. We're going to take those guide hairs, use their motion to figure out decent positions for all the other hairs. Then there's a correction step. And if you notice, some of those nice hairs actually travel across the head. We're actually going to do some simulation, some low, very fast simulation on all the hairs in order to correct them. And it has to be super fast, because we're going to be doing simulation on 100,000 hairs. Yeah, they use parallelism like crazy in this picture. Right? All right. So we're going to have a skinning model. And the skinning model is actually pretty easy. First, we have to define one more thing. S star is the rest state for all hair particles as the static equilibrium state when the head is static. So S star is equal to the rest state of a hair particle. So S is just a general world coordinate of the hair particle as it travels through time. S star is specific in that this is the local, and it's in local frame of reference, I believe. Local frame of reference, this is where the hair wants to be, is its rest state. You want to go back to that if we ever stop our head motion. All right? So consider a simulation step in which the head transformation T and the guide hair particles are moving to their current states S sub G. So say we turn this head and we move things, and we actually simulate the guide hairs. And each one of these guide hairs, that's a G, has an S sub G, a whole bunch of S sub Gs for the particles associated with each one of these guys. Remember, S is the position and orientation of each one of the particles associated with hair. For each guide particle G that we move around here, we first compute a local transformation model. We're going to do this. I'm just gonna write it down. S bar G. What? For each guide particle, so a particle associated with a guide, we first compute a local transformation B sub G. So this, each one of these is, that's a G1, this is G2, this is G3. So each one of these guys has a B associated with it. That transforms it from its rest state to its current state in the local frame. So wait, what? This is where you have to write this stuff down. S bar means that the particle is in the local frame reference. So this is where the head is at the origin pointing down the x-axis. So SG is the particle location after we run a simulator, right? So that's the world space location of the particle after you run a simulator. To put this back into its local frame of reference, we just have to invert the head transformation and whoosh, we move it back to the origin, right? So this takes the transformation that took the head out into world space and inverts it. So we put it back. So this takes the simulated position of our particle and moves it into local space. It's actually pretty easy. But what we want to compute is this thing that says, all right, how did this particle move from its rest position? This is where it is just hanging when the head hasn't moved, to where it is where we simulated it to in local space. And so B sub G is just saying, how do I take my particle in rest position in local space and move it into the position that it's at after we do a simulation in local space? Does that make sense? So you know, I'm moving my head around. I move the hair in world space. I push that back so that it's in its spot in local space. And then I just have a single transformation that takes where it was in its default position into the transformation position. So it's a little bit of, so where is this coming from? And there's enough information in here because this is position and orientation. It's a state that has a P and a T to compute this. They don't even give any math for computing this because it's easy. This is something that we can easily do once we know the local position of the simulated particle and its rest position. Easy peasy. Not a problem. Okay. So now, these are guide hairs. What about all the rest of the hairs? To interpolate the state of any hair, we're going to go S sub I. What do? Well, first of all, we have T. We spend a lot of time making sure that all this stuff is happening in local space, where the head is at the origin, pointing down to the x-axis. So we're going to do some interpolation, we're going to do some skinning, and then we're going to transform it back into world space. So that's what that T does. The next thing is sum, and this is where we're going to get really interesting. CI. CV, S, I, yep, star. All right. Making sure that I got everything right. Yes. Wait, what? All right. So let's first of all look at this. What are we? So we know what the T is. That just moves us back to world space. No problem. We're summing over a whole bunch of G's. And G's are guide particles. They're not guide hairs. Each one of the guide hairs is a certain number of guide particles associated with it. And there are a bunch of guide particles that are going to influence particles in our hair. And this is one thing right off the bat that this paper is doing, is that it's treating each hair as a collection of particles, and it dives right down into dealing with them as just particles. So if I've got a particle, a point on the hair that I'm interpolating, this point is going to start using particles in its neighborhood. Well, actually, I should draw it up here like this. So I'm grabbing some of those guys as well. So this particle might be using this guide particle, and this guide particle from this hair, and this guide particle, and this guide particle from that hair, in order to figure out its position. Then, what are we doing? We've got this SI. We know the local position of the particle that we're working on, that green guy. We know where it is in its rest pose. And we're going to take the B that we computed up here for each one of these particles on the hair that it's associated with, right? And we're going to weight it. So we're going to transform this particle by the same transform that we computed for this guy, and transform the particle by the same transform that we computed for this guy and all these guys. And there's this mysterious weight that we're using to sort of average out the results.
You know,
Yeah.
what are they doing to keep alignment with the ECGs? Those coordinate frames, they parallel transporting fixed vector along the curve or something?
Well, they're really relying on this stuff here. So since they have this,
You can't. I mean, if it's just a tangent direction, you can construct a coordinate frame, but there's no guarantee about what way it's twisted.
well, you know. So if I've got a particle chain, so what Ron is asking is, wait a second, let's look a little bit more carefully at this. For every particle S, I have a position, and I also know where I am in the chain. So I can easily compute that, and from that I can create a cross product, so I can get a nice little particle frame out of this, right?
I mean, the tangent, yes, but the normal, you pick the direction.
I kind of assume that they have this. They're pulling that out of the groove from the default state, because we do that as well. Parallel transport is an idea, and that's something that possibly could be, but there are problems with parallel. Are there problems with parallel transport? Does that stuff out? No, there are no problems with parallel transport. Quite frankly, yeah. We could layer on this. You know, if they assume you can do this with just one extra vector, but screw it, you can make this a full-on 3x3 matrix if we want. Now let's assume that we have an actual 3x3 matrix at this point, because that's details. It's important details, but let's assume that we can figure out the orientation of the particle, because it is important details. Okay, so this thing is how we're going to move the particles of all the hairs. So 100,000 particles of the hairs. So think about what Ron was talking about, the whole simulation thing. We're going to simulate these red hairs, the guide hairs, using some fast simulator. And then we're going to apply the motion of those guide hairs to the rest of these guys very rapidly. So we're going to calculate this really quickly, compute all the BGs, and then think how fast you can do with this. And to figure out the position of any particle in the hair, all you have to do is go through their list of neighboring guide hairs, multiply by this mysterious weight, multiply by this that we've already calculated, and multiply by their rest position. So this can be done really, really fast. Fingers crossed. That's what the paper maintains, is that we're doing a very dead nut simple hair skinning model in order to move the hairs. There are two things that are floating around here. First of all, what is that? Which particles do we use? That's very ill-defined. How do I know which particles are the best for me to determine the position of that particle on that hair? And then also, these weights. How do we compute those weights so that they're the best? That's what this whole paper is. They say, let's run some full-on hair simulation, and then use that full-on hair simulation to calculate optimal weights for each particle in our 100,000 hairs. And also calculate the optimal group of points surrounding that particle that makes that particle move as best as possible.
Question.
Yeah,
The optimal group of points, is that among any possible strands or just among guide strands?
Guide strands.
Then there's one more thing that we need to do, which is figure out which are our guide strands.
Exactly. Thank you very much, Cyrus. Yes, the question that's also something that I just popped out. Like I was talking about, these guide strands. They aren't the groom guide strands. How do we figure out? So that's the thesis of the paper. That's the thesis of the paper. Is they say, for any hair simulation system, we are going to try to figure out the optimal guide strands, the optimal combination of points in the guide strands, and optimal weights for all the points in the hair so that it works the best for the simulations that you've given us. And once I have that, then I can run this where all I have to do is simulate the guide strands, and I can get a reasonable simulation for 100,000 or 200,000 hairs in real time, or very close to real time. Now, there is one other step that they do not shy away from, because there is a correction step, and I mentioned this before. You have to correct this, because this is only going to get you so far. If you do this, and you're computing all these hairs, you might actually interpolate a hair into the character. You might have a collision, or you might have a hair-to-hair collision, or however you want to do it. That this might not look perfect. But what they say is, if we can get this close enough, the correction step can be done very fast. We don't have to do a full-on simulation in order to correct all these hairs. Because we've gotten close enough, and because we've done some very interesting partitioning of our hairs, we can actually do this correction step in full parallel really fast. And we'll see if we can get to that in this one, but we'll see. All right, so this paper, by the way, is lovely. It's a beautiful paper, easy to read. You know, there's definitely, you have to keep track of your hats and stars and stuff like that, but it's, if you're at all interested in this, it seems like relatively simple to implement once you finally get it all. Oh. Okay, so step one, guide hair selection. Hair selection. And that's actually the biggest thing here. We have a training data. We have this huge, a large selection of frames that we can look at. What we want to do is figure out a subset of all these hairs. So let's actually draw this out. We have, the head has moved, and we've got our hairs flying away. There's motion as this head moves, and what we want to do is, in the 100,000 hairs on the head from our full simulation, we want to figure out a subset of those hairs that kind of break the hairs into groups that move similarly. It's the kind of thing that we're going to be doing a great big similar motion search. Right? So, how the hell do you do that? And this is actually a really interesting question. It's like, I've got 100,000 hairs in my head, and I've just flipped my head. So I've got, well, my head's no big deal, but somebody with long hair especially. You flipped your head, and all of a sudden all the hairs are just going blam. How do you determine whether one hair is moving similar to another? Now, yeah, we're going to figure that out. It all starts out with a graph. So we first build a graph model that reflects the local motion similarity of hair strands. All right, now bear with me because this gets a little complicated, but it's not that bad. So on the graph, every node represents a hair particle. So if I have a particle here, we're just going to put a particle, and we'll call it P. That is a hair particle, and that's going to be a spot on the graph. All right? We initialize the graph edges by considering hair particle proximity. So Pi sub f is equal to the position of a particle I, let's put an I there to say that that's particle I, at frame f. Remember, we have a full-on hair simulation that we have 500 or 1,000 frames of hair simulation. For every particle I at frame f, we search its nearby particles within a radius r and create an edge between them. So I've got a thing here that says P, let's go, we're going to concretize it. Particle 10 has a node on this graph. For every particle I at f, we search nearby particles within a radius RL and create an edge between them if the distance between those two particles is within RL. So if there is a Pj here that comes within RL at any point in our simulation, we're going to create an edge between that character. So let's say that's P13 and this is P10. If at any point during our simulation those guys get within RL of each other, create an edge between those two guys. Not only do I do that, but I also count how many times in our simulation these guys come within RL of each other. So as I go through each frame, I might put in it, and the first time I see them come within each other, I put an edge there, and I put that as 1. But then maybe 2 frames later, if they come within RL again, I'm up that to 2. So there is a count that's associated with the number of times they are RL apart is associated with that. So there's this value, just put it at 2. All right. So far, so good. So all of a sudden, you start thinking about this. Let's put concrete terms. 100,000 hairs, maybe, let's make it easy, 10 particles per hair. That's reasonable. So that's an extra 1. There are this many particles in our simulation. Remember, we're looking at every single frickin' hair at this point. We don't have guide hairs or normal hairs. We just have hairs because we've run this full simulation and we just have 100,000 hairs. So we have 1,000,000 particles that we have to do. And all of a sudden, we've got a graph with 1,000,000 nodes in it. And there are a lot of edges. You know, as these guys move back and forth here, you get, you know, a bazillion particles. There's going to be, I'm not going to draw 1,000,000 particles, but you can imagine that some particles are going to have edges, and some particles are going to have a lot of edges, and you're going to have this very connected graph about particles that get close to each other, which is kind of cool, all right? So that's kind of neat. All right, now, in the next couple of paragraphs, they talk about efficiency, because they realize that number is big. So, to enable efficient use of graph algorithms, we further prune the graph edges by removing edges whose counts are smaller than some threshold. And the threshold is f, which is the number of frames, equals 1,000 frames, let's say, because it makes it easy. And then they have a threshold where they say if your count c is less than epsilon times f, then we're just going to throw that kind of edge away. We won't throw the particle away, but we'll just remove one of those things. And where E is 0.2. So 0.2 would be 200, right? So unless, if I've got an edge where these two particles only came within RL of each other 17 times through the entire simulation, I'm going to erase that edge, make this a little bit easier to deal with. All right. Okay, so far so good. Remember, this is actually cool. This is an analysis of how hairs move, and this is something that even if we don't do this full simulation, this is a kind of a neat way of doing this. So now we want to see so right now we've got a graph that says, hey, these particles are close to each other. They come close to each other, at least spatially, somewhere along the way in 1,000 frames of simulation. But now we want to decide whether or not these particles are actually moving similarly to each other. Rather, whether or not these particles just happen to cross in front of each other, or whether these particles actually travel together as they move. You know, they're part of a clump, or they form a clump long enough that we really want them to be partners. All right. So in order to do that, we're going to compute this weight. So consider a particle I at time frame. So we're going to create, I'm just going to write this down. U sub I j equals the sum negative of f over all the frames. So this is, we're going to go over every single frame of our simulation. And we are going to look at particles that share an edge, right? So we're going to take just hold on while I type this out, minus E, J, F. This actually does make some sense. I star squared, right? Plus, I'm going to just go, plus S, J, F, minus B, I, F, S, J, star, squared, plus C, that's C, okay, what? Oh, there's a parenthesis here, sorry. Okay, remember what we were talking about. So, oops, I forgot bars. We now go over to our handy dandy little thing. This is the hair in the rest position at its local frame, right? Hair particle. And notice the indices. This is the ith particle and the jth particle. And I and j are particles that share edges. They've come close enough to each other enough times so that we want to, they're actually got an edge between them. And what we're going to do is go for each frame and say, hey, if I take the transformation that moves j, notice the j, from its rest frame to its current position, and apply that transformation to I. So I use the transformation that moves the particle j from its rest position to its current position in local space. And I apply that actually to the ith frame. Then, how close do I actually get to the actual location of the ith particle? So if I move the ith particle as if it was moving like j, how close do I actually get to the ith particle? And vice versa. If I move the jth particle as if it was moving like I did, how close do I get to the actual location of the jth particle? Crazy math, but it actually makes sense, right? This guy's moving in one way, and this guy's moving another way. If they are both moving similarly, applying the same motion here gets you close to that guy. You know, they're sharing the same things. If they're moving in opposite directions, you're just going to accelerate that, right? You're going to push them farther apart. So this is a nice way to measure whether or not these two particles are actually moving in lockstep, if they're actually moving along. You could also, I could imagine you could compare the matrices. You could do a Frobenius norm or something of the matrices, but this was a clever idea. I thought this was kind of cool. Then, what they do is they actually have a negative sign on here. So if you're actually moving close to each other, this value is going to get small, right? And then there's this constant up here. What the constant is there is to ensure that this value is always positive. So they pre-compute this constant to be the maximum value that this computes at any frame in here. So they say, somewhere along there's going to be the biggest distance that they get. I'm going to compute that so that when they get really far apart, they sort of flip this around. So that if they get far apart, this is going to produce something that's close to 0. But when they're 0 apart, when they're really close to moving together, they're going to produce this very large value. What they want is this to be big when they're moving in lockstep and small when they're moving against each other. They're not moving the same way. And so they do a little pre-calculation where they do this once before to figure out the biggest value that they possibly get. And then they put a negative sign in there to sort of invert this whole thing. Easy. So think about what we now have. We have particles that are collected. We have a count associated with them, that these particles have been close to each other for 500 frames. And we have a U associated, a Uij, that says, how strongly are these guys moving together? Are they part of the same group? And we have that for every single edge in here. Now notice, you're thinking, oh my God, this is going to take forever to compute. And yeah, who cares? This actually takes a long time to compute. But this is a pre-processing step. We do this in order to get this thing going fast. Okay, so now this is really cool. We have a graph, million particles in there, whole bunch of edges that we've pruned. We got rid of some of the edges, and all these edges have weights. And you look at it and you go, okay, now what? Now, there are tools out there. This is actually, what we're going to do is a classical minimum. It's called minimum K partition. What we want to do is partition this graph into K groups, where K is the number of guide hairs that we want, right? We want to, oh wait, hold on. I skipped the whole paragraph and it's important. Once we've done this, before applying our guide hair selection algorithm, these are all particles. We're actually going to collapse this graph down. We finally shrink the size of the graph. We contract all hair particle nodes that come from a single hair. So if all these particles are part of the same hair, we're going to shrunk them down into one connection, or one particle, and then keep the connections between them. You know, if this one and this one all share connections, we're just going to sort of scrunch them all into one connection that goes in there. So we're going to scrunch this down so that there's only one particle per hair. The connections that we created are still maintained. We sum the weights of the edges, these guys that we computed, so that we have the edges sums are maintained. After this step, we have a graph whose nodes correspond to individual hair strands. Our next step is to cluster that graph into groups and select representative node from each group as a guide hair. Okay, so that makes sense. Went fast, right? Here we have a graph of million particles. Now we shrink them down, and now we have a graph of 100,000 hairs. And we do some math on this. It's just a sum of the weights associated with each edge, so that we still maintain that connectivity information that we computed. All right, so now, this is what we want. We say, I have a hair simulator that can simulate 100 guide hairs in real time. So I'm going to type into my minimum K partition tool the value of K being equal to 100. And what it will do is go through, it does a cool little thing. It tries to find groups of this where if I had K of 2, where the shared edges between the groups are smallest. The smallest of all possible things. Now to do this is an NP-hard problem. An NP-hard means that it's really, really hard. The only way to create a completely optimal solution is to search all possible things. And with 100,000 hairs, that will take a very long time indeed. But we don't care that much. This is hairs. And so there are some optimizations that you can use. There's some greedy algorithms, and in fact, they use we adopt a approximated K-cut algorithm, which provides fast performance and guarantees bounded approximation results. We use this thing from a library called METIS. So they just sort of said, screw it, somebody else has figured this out. Type in the number K, run this on that, and it produces groups where the edges inside the groups are really strong, and the edges between the groups are as small as possible. So you can assume that inside this group, the hairs are moving in lockstep. Remember, they're all connected inside here. They're all share, this guy is moving very similar to the next guy. And that these two guys are not moving similarly at all. They're moving very differently because their edge connection is very small indeed.
So that library you mentioned, I assume that the authors of that library were just attacking general clustering problems.
Totally
doesn't have
general.
anything to do with hair.
Nothing to
And
do
so
with hair.
something that I think is really interesting about this kind of motion clustering approach is that, as far as I can tell, and you can correct me if I'm wrong, as far as I can tell, the only thing about this that is hair specific was that reducing graph nodes that are on the same strand into one. But if you didn't do that optimization, then presumably you could apply this to other types of motion clustering, like anything that you could represent as these particles. And the definition you made of the particle is point and, coordinate frame, right?
Could you apply this to any kind of particle system?
Yeah, that's
or muscle simulator.
exactly right.
Actually,
Facial motion.
there
Dude.
is literature out there. The generic method underlying all of this was in a form of K-means clustering in a paper called the Skinning Mesh Animations.
Son of a what?
Yeah, this one, the clustering technique over here seems rather complicated than the one in Skinning Mesh Animations.
Well, it wasn't complicated for them. They just made the library compile and they press go. Now, this does take hours, by the way. This is not interactive at all. This is like, it's going to take a long time to do. But think about what you got out of this. This is really cool. We group this thing into blobs of hairs that move in a similar fashion over a sequence of 1,000 frames. So this is kind of cool. And you can control it. If I have a faster hair simulation, I can crank that K up into 1,000 or whatever. Right? This is all very tunable.
One question. It defines one specific guide hair only that will fully represent another hair. Does it reduce it to only, is the number of guide hairs that they're attached to variable? Does it vary it?
That is one thing that I was thinking about as I was reading the paper. Like, if you have different motions, could you have different clusters for different kinds of motion? And at this point, they are doing one cluster for the entire sequence.
But also, does any specific hair have to have multiple guides that it's attached to, or will it reduce it down to like a single guide hair?
No, they always have multiple guide hairs. So we're gonna figure out how they choose guide hairs. Remember, there are three things: guide hairs, the points on the guide hairs that affect the point on the hair, and then the weights associated with it. So right now we're just choosing guide hairs for the whole system, sort of optimal guide hairs for the whole system. The next step is to figure out which points on those guide hairs work best in order to interpolate a point on a normal hair. And that is constant throughout the entire, they don't change that either. And then you have the weights associated with that. And again, those aren't animated anywhere. These are all constant values that are associated, or that are computed for that entire sequence that seem to work the best for all aspects of the sequence. That's what I would like to propose at the end of this, is that we can change that. And there's a follow-on idea at the end of this, which we aren't going to get to today because we're coming up to, yeah, in fact, this might be a really good point to stop. Yeah, we're going to stop. We're going to stop. So next week, we will continue on this because this is a fun paper. And likewise, I encourage anybody who's interested to read the paper, and then you can help me along with this. And then after that, Nafis, who's actually watching this, this probably is going to be either on the July 4th week or the week after that, because July 4th week, that's going to be a weird time to do a chalk talk. Nafis is going to do his SIGGRAPH paper score. And then I was going to, Cyrus is in the room. There's still time to do you want to do a practice talk for one of your papers?
Potentially.
Okay. Potentially. Yeah. First rule of chalk talk, no pressure ever. I love doing this stuff. All right, so we're going to stop right now. Put a little pin in that. And next time we come back, we're going to figure out inside these clusters which one of these hairs is the best guide hair. And there's going to be more.
Thanks.